Hi everyone, welcome to NCERT Audiobook, Unit 9, Hydrogen. Hydrogen, the most abundant element in the universe and the third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as a diatomic molecule and is called dihydrogen. It forms more compounds than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance, as you will learn in this chapter. 9.1 Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that the elements in the periodic table are arranged according to their electronic configurations, hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration of alkali metals, which belong to the first group of periodic table. On the other hand, like halogens with Ns to Np5 configuration belonging to the 17th group of the periodic table, it is short by one electron to the corresponding noble gas configuration, helium. Hydrogen therefore has resemblance to alkali metals which lose one electron to form unipositive ions, as well as with halogens which gain one electron to form uninegative ion. Like alkali metals, hydrogen forms oxides, halides and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Delta Hi of lithium is 520 kJ per mole, fluorine is 1680 kJ per mole, and that of hydrogen is 1312 kJ per mole. Like halogens, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogens, it differs from them as well. Now the pertinent question arises as where should it be placed in the periodic table? Loss of the electron from hydrogen atom results in nucleus H plus of 1.5 × 10 − 3 picometer size. This is extremely small as compared to normal atomic and ionic sizes of 50 to 200 picometer. As a consequence, H plus does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is therefore best placed separately in the periodic table. 9.2 Dihydrogen H2. 9.2.1 Occurrence. Dihydrogen is the most abundant element in the universe, 70% of the total mass of the universe, and is principal element in the solar atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it is much less abundant, 0.15% by mass, in the Earth's atmosphere. Of course, in the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrides, including hydrocarbons and many other compounds. 9.2.2 Isotopes of hydrogen. Hydrogen has three isotopes: protium H11, deuterium H12 or D, and tritium H13 or T. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinary hydrogen, protium, has no neutrons. Deuterium, also known as heavy hydrogen, has one, and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156% of deuterium, mostly in the form of Hd. The tritium concentration is about 1 atom per 10^18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta minus particles, T half 12.33 years. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reactions, mainly due to their different enthalpy of bond dissociation. However, in physical properties, these isotopes differ considerably due to their large mass differences. 9.3 Preparation of dihydrogen H2. There are a number of methods for preparing dihydrogen from metals and metal hydrides. 9.3.1 Laboratory preparation of dihydrogen. 1. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. 2. It can also be prepared by the reaction of zinc with aqueous alkali. 9.3.2 Commercial production of dihydrogen. The commonly used processes are outlined below. 1. Electrolysis of acidified water using platinum electrodes gives hydrogen. 2. High purity greater than 99.95% dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. 3. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reactions that take place are: at anode 2 chloride aqueous gives chlorine Cl2 plus 2 electron. At cathode, 2 moles of water gives H2 plus 2 OH minus. 4. Reaction of steam on hydrocarbons or coke at high temperatures in the presence of catalyst yields hydrogen. The mixture of CO and H2 is called water gas. As this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbons, it is also called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspapers, etc. The process of producing syngas from coal is called coal gasification. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixture with steam in the presence of iron chromate as catalyst. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. Presently, 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solutions, and 1% from other sources. 9.4 Properties of dihydrogen. 9.4.1 Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical properties, along with those of deuterium, are given in Table 9.1. 9.4.2 Chemical properties. The chemical behavior of dihydrogen, and for that matter any molecule, is determined to a large extent by bond dissociation enthalpy. The HH bond dissociation enthalpy is the highest for a single bond between two atoms of any element. What inferences would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atoms is only 0.081% around 2000 Kelvin, which increases to 95.5% at 5000 Kelvin. Also, it is relatively inert at room temperature due to high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It accomplishes reactions by 1. Loss of the only electron to give H+, gain of an electron to form H-, and 3. Sharing electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reactions. Reaction with halogens. It reacts with halogens X2 to give hydrogen halides HX. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. Reaction with dinitrogen. With dinitrogen it forms ammonia. This is the method for the manufacture of ammonia by the Haber process. Reactions with metals. With many metals it combines at a high temperature to yield the corresponding hydrides, where M is an alkali metal. Reactions with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metals less active than iron into corresponding metals. Reactions with organic compounds. It reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, 1. Hydrogenation of vegetable oils using nickel as catalyst gives edible fats, margarine and vanaspati ghee. 2. Hydroformylation of olefins yields aldehydes which further undergo reduction to give alcohols. 9.4.3 Uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soybean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol. It is widely used for the manufacture of metal hydrides. It is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. Atomic hydrogen atoms produced by dissociation of dihydrogen with the help of an electric arc are allowed to recombine on the surface to be welded to generate the temperature of 4000 Kelvin. It is used as a rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases greater energy per unit mass of fuel in comparison to gasoline and other fuels. 9.5 Hydrides. Dihydrogen under certain reaction conditions combines with almost all elements except noble gases to form binding compounds called hydrides. If E is the symbol of an element, then hydride can be expressed as EHX, example MgH2, or EMHN, example B2S6. The hydrides are classified into three categories. 1. Ionic or saline or salt-like hydrides. 2. Covalent or molecular hydrides. 3. Metallic or non-stoichiometric hydrides. 9.5.1 Ionic or saline hydrides. These are stoichiometric compounds of dihydrogen formed with most of the S-block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as LiH, BeH2 and MgH2. In fact, BeH2 and MgH2 are polymeric in structure. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of hydride ion. Saline hydrides react violently with water producing dihydrogen gas. Lithium hydride is rather unreactive at moderate temperatures with O2 or Cl2. It is therefore used in the synthesis of other useful hydrides. 9.5.2 Covalent or molecular hydride. Dihydrogen forms molecular compounds with most of the p-block elements. Most familiar examples are CH4, NH3, H2 and HF. For convenience, hydrogen compounds of nonmetals have also been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative numbers of electrons and bonds in their Lewis structure into electron deficient, electron precise and electron rich hydrides. An electron deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane is an example. In fact, all elements of group 13 will form electron deficient compounds. What do you expect from their behavior? They act as Lewis acid electron acceptors. Electron precise compounds have the required number of electrons to write their conventional Lewis structures. All elements of group 14 form such compounds. Example CH4, which are tetrahedral in geometry. Electron-rich hydrides have excess electrons which are present as lone pairs. Elements of group 15 to 17 form such compounds. Ammonia has one lone pair, H2O2 and HF3 lone pairs. What do you expect from the behavior of such compounds? They will behave as Lewis bases, that is electron donors. The presence of lone pairs on highly electronegative atoms like nitrogen, oxygen and fluorine in hydrides results in hydrogen bond formation between the molecules. This leads to the association of molecules. 9.5.3 Metallic or non-stoichiometric or interstitial hydrides. These are formed by many D block and F block elements. However, the metals of group 7, 8 and 9 do not form hydride. Even from group 6, only chromium forms chromium hydride. CRH. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. For example, LH 2.87, YBH 2.55, TIH 1.5 to 1.8, ZRH 1.3 to 1.75, VH 0.56, NIH 0.6 to 0.7, PDH 0.6 to 0.8, etc. In such hydrides, the law of constant composition does not hold good. Earlier it was thought that in these hydrides, hydrogen occupies interstices in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, cerium, and actinium, other hydrides of this class have lattice different from that of the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction or hydrogenation reactions for the preparation of large number of compounds. Some of the metals PDPT can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and as a source of energy. 9.6 Water. A major part of all living organisms is made up of water. Human body has about 65% and some plants have as much as 95% water. It is a crucial compound for the survival of all life forms. It is solvent of great importance. The distribution of water over the Earth's surface is not uniform. The estimated world water supply is given in table 9.2. 9.6.1 Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in table 9.3 along with the physical properties of heavy water. The unusual properties of water in the condensed phase, liquid and solid states are due to the presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization and high heat of fusion in comparison to H2S and H2SE. In comparison to other liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment, and dielectric constant, etc. These properties allow water to play a key role in the biosphere. The high heat of vaporization and heat capacity is responsible for moderation of climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water. 9.6.2 Structure of water. In the gas phase, water is a bent molecule with a bond angle of 104.5 degree and OH bond length of 95.7 picometer as shown in figure 9.1a. It is a highly polar molecule. Its orbital overlap picture is shown in figure 9.1c. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperatures it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation, which ensures the survival of the aquatic life. This fact is of great ecological significance. 9.6.3 Structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure as shown in figure 9.2. Examination of ice crystals with X-rays shows that each oxygen atom is surrounded tetrahedrally by four other oxygen atoms at a distance of 276 picometer. Hydrogen bonding gives ice a rather open type structure with wide holes. These holes can hold some other molecules of appropriate size interstitially. 9.6.4 Chemical properties of water. Water reacts with a large number of substances. Some of the important reactions are given below. 1. At amphoteric nature. It has the ability to act as an acid as well as a base, that is, it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with ammonia and a base with H2S. The autoprotolysis, self-annihilation of water takes place. Redox reactions involving water. Water can be easily reduced to dihydrogen by highly electropositive metals. Thus, it is a great source of dihydrogen. Water is oxidized to O2 during photosynthesis. With fluorine also, it is oxidized to O2. 3. Hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. Hydrates formation. From aqueous solutions, many salts can be crystallized as hydrated salts. Such an association of water is of different types, with 1. Coordinated water, 2. Interstitial water, example BaCl2 twice H2O, 3. Hydrogen bonded water, example CuH2O whole 4 2 plus SO4 2 minus dot H2O in CuSO4 dot 5 H2O. 9.6.5 Hard and soft water. Rainwater is almost pure, may contain some dissolved gases from the atmosphere. Being a good solvent, when it flows on the surface of earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with soap easily. Hard water forms a scum precipitate with soap. Soap containing sodium stearates reacts with hard water to precipitate out calcium magnesium stearate. It is therefore unsuitable for laundry. It is harmful for boilers as well. Because of deposition of salts in the form of a scale, this reduces the efficiency of the boiler. The hardness of water is of two types, temporary hardness and 2. Permanent hardness. 9.6.6 Temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonates. It can be removed by 1. Boiling. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium hydroxide, and calcium bicarbonate is changed to insoluble calcium carbonate. It is because of high solubility product of magnesium hydroxide as compared to that of magnesium carbonate that magnesium hydroxide is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. 2. Clark's method. In this method, calculated amount of lime is added to hot water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. 9.6.7 Permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by following methods. 1. Treatment with washing soda, sodium carbonate. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonates. 2. Calgon's method. Sodium hexametaphosphate Na6P6O18, commercially called Calgon. When added to hard water, the following reactions take place. The complex anion keeps the Mg2 plus and Ca2 plus ions in solution. 3. Ion exchange method. This method is also called zeolite permutate process. Hydrated sodium aluminum silicate is zeolite or permutate. For the sake of simplicity, sodium aluminum silicate NaLSiO4 can be written as NaZ. When this is added in hard water, exchange reactions take place. Permutate zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with an aqueous sodium chloride solution. 4. Synthetic resins method. Nowadays, hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin RSO3H is changed to RNA by treating with NaCl. The resin exchange Na plus ions with Ca2 plus and Mg2 plus ion present in hard water to make the water soft. Here R is resin anion. The resin can be regenerated by adding aqueous NaCl solution. Pure demineralized water free from all soluble mineral salts is obtained by passing water successively through a cation exchange and an anion exchange resins. In this cation exchange process, H plus exchanges for Na plus Ca2 plus Mg2 plus and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, OH minus exchanges from anions like chloride, bicarbonate, sulfate, etc. present in water. OH minus ions thus liberated neutralize the H plus ions set free in the cation exchange. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively. Okay, that's all for today. Next video में hydrogen peroxides पढ़ेंगे. Thanks.